Okay, now I'm going to share my screen with you. As I said last at the first meeting, really my objective is that you guys first enjoy the class and we all learn together. So please don't be shy. Don't hesitate if you have any question. We are here to learn together, and even if you think your question could be a kind of stupid question, definitely there is no stupid question, and feel free to ask me questions. Either I know the answer, I tell you right directly, or I will provide the answer after the class. So don't worry. Today we are going to talk about pre-treatment and the physical and chemical conversion of biomass. But why pre-treatment is important for biomass conversion? And this is why we are going to discuss it today. So, what we are going to learn today at the end of the class, if we finish today, if not next time, we will finish the chapter because it's quite lengthy. We have two objectives. First objective is to understand the importance of pre-treatment in biomass conversion and to know the different types of pre-treatment that exist in biomass conversion. So pre-treatment, which means a treatment before the main conversion of biomass. So second objective is to explain the concepts between the techniques, okay, and to understand what is each uh, physical treatment, chemical treatment, the related characteristics of biomass that are involved, and at the end we are going to find out which pre-treatment is advantageous plus its disadvantages over other techniques. Okay, so uh, here is the structure of the course that we are going to talk in this chapter. After talking about importance of methods of pre-treatment, we are going to start with physical treatment and conversion of biomass, essentially by drying, grinding, and densification. Okay, extremely important processes, not just for biomass conversion, but also in any other field where you have a solid material. Just before I continue, I would like to emphasize that uh, biomass, most of the time, okay, let's say 99% is solid. Okay, we are talking about the solid material. Okay, so uh, when you are dealing with solid, uh, there are some steps that you have to do. You have no choice. You have to. There are some steps that you have to do to make that solid ready for next steps. Okay. In other words, uh, if you don't do these kind of physical pre-treatments, you cannot be successful. So we are chemical engineers. Traditionally, most of the chemical engineers, they are used to oil, like I mean, liquid and solid, like oil and gas systems, uh, liquid and gas, yeah, oil and gas systems. But when it is about the solids, when the reactant is a solid, chemical engineers are a little bit uh, in doubt because there are parts of the solids that are related to mineral processing, metallurgical engineering, and students especially might think that it is not in their field. Also, there are some physical treatments that are really mechanical treatments, and you might think that this is part of mechanical engineering. sort of duties, but it's not true. Your chemical engineer is a type of engineer who is going to, or who is able to handle any process for whole range of material, solid, liquid, gas, even plasma. Okay, that's the power of chemical engineers. So in biomass conversion, we are dealing with solid materials most of the time, and these solid materials in the processing, either we use a liquid phase or a gas phase, depending on the process. So, and a new challenge in biomass conversion is that usually we are dealing with two-phase or multi-phase systems. I mean, not just only solid or only liquid or only gas. It's solid plus liquid, solid plus gas, or solid plus liquid plus gas. We have multi-phase systems in biomass conversion quite often, and that could be a challenge. But of course, in biomass conversion, uh, we are you are just in this course. I mean, you are going to just get an idea of different aspects of biomass conversion. Hopefully, when you are um, at, for example, graduate level, master or PhD, or even if you work at a company uh, that deals with solid materials, hopefully you get more insights into the processing solids and you get more expert. Of course, uh, beside during this course, in any case you have any uh, it's a specific question, advanced question, whatever, feel free to email me after the class. I'll be happy to answer you. Okay, I needed to give you this introduction because, in my opinion, if you really know the objective, if you really know the message of the course, then you will be happier and you will be more excited to follow the course. Otherwise, if you don't know why you are at the class, you don't enjoy it. I hope you agree with me. So that's why when I talk about drawing, grinding, and densification, I want you to really pay attention when I'm there because they are extremely important for biomass conversion. By the way, beside physical pre-treatments of biomass, we are going to talk also about some chemical pre-treatments of biomass. But most specifically, we are going to talk about hydrolysis or hydrolysis, chemical hydrolysis, and thermochemical hydrolysis. We will later we'll discuss what they are. Of course, there are other pretreatment methods, other chemical pretreatment methods other than hydrolysis. For example, ozonolysis or hydrogenolysis. There are other things, depends on the chemical reactant. When we say hydrolysis, hydro means water, okay? Usually LYSE or in English LYSIS, they are talking about cracking. You want to break a bond. You want to break a molecule and make it a smaller molecule, or uh, make a small molecule and then a small molecule react together to form a new material. So lease or lysis in English always stand for cracking, breaking a bond. But the prefix tells you what is the tool for breaking the molecule. When you say hydrolysis or hydrolysis or hydrolysis in English, hydro means water. When we say pyrolysis or pyrolysis, pyro means heat. It means you are using energy, heat, high temperature, pyrolysis. When you say hydrogenolysis, it means that you are using hydrogen to break the bonds. So these are the terminology that in especially in biomass conversion you might face. So when we say hydrolysis or hydrolysis, it means you are going to break a bond with water molecules. Okay. So in hydrolysis, chemical hydrolysis systems, we use acids or alkali reagents or organics and also a specific sorts of uh, solvents that we call it liquid ionic or ionic liquids. We will discuss later. And also we are going to talk about thermochemical release, and we will see how they look like. Okay, I spent too much time, almost half an hour on introduction because I really feel it is important. Once you know the message, once you know why we are in the class, you follow the course. Otherwise, not at all. So the diagram here is very interesting diagram because it again it tells you why we are at this class and what we are going to learn. So we are talking about biomass. As we said before, we have different sources of biomass like agricultural residues, food residues, forestry residues, municipal or industrial waste, any even biodegradable materials. They are all biomass, and we want to convert biomass with a conversion process, with a specific process to make biofuels and energy. Okay, but of not necessarily biofuels. There are recently also biomaterials that are used that are produced from biomass, but traditionally biomass has been used for biofuel and energy production. And there are different different processes for biomass conversion, like biochemical processes with bacteria, with enzyme, chemical processes, thermochemical processes, thermal and physical processes. Okay, next week I will ask you what is the difference between chemical process, thermochemical process. Because I hope you understand what is the difference between each of these processes. But next time we will discuss this. Keep your mind, you need to practice what they are. So before I have to say something. So once you have biomass, let's say you have harvested biomass from the field, you cannot just directly use biomass for in a processing plant because there are a lot of things associated with biomass, associated with physical and chemical properties of biomass that we have to take into consideration in order to provide biomass ready for conversion. And those kind of uh, uh, considerations that we need to take, we call them pre-treatment. So we have physical and chemical pre-treatments for before processing biomass to be converted to our target product. So this slide is very important and interesting slide that tells us about the role of pre-treatment, why we do pre-treatment. So this is the beautiful picture of biomass. Lignocellulosic biomass, in fact, that tells you how cellulose, hemicellulose, and lignin are kind of arranged together. As you see, for example, this kind of light yellow color is cellulose, and cellulose is wrapped up by kind of mingled kind of uh, shape of hemicellulose, and uh, and you can see that hemicellulose is kind of holding cellulose materials together. And then cellulose and hemicellulose are covered by lignin. So lignin is a kind of protection layer around hemicellulose and cellulose. Okay, this is a nice picture that tells you how a woody biomass looks like. But let's look at this picture. This is a bit more schematic of woody biomass. So you can see that how cellulose is the kind of long chain. Sometimes, most of the time, cellulose has a crystalline structure, but sometimes it has amorphous structure. That's why it's not like a straight line. It tells that it is a kind of amorphous structure, which are anyway all cellulose polymers are together with hemicellulose. So as you see, always there is a wall of lignin that is holding the biomass. So what we are going to do in pretreatment, in fact, we want to destroy this wall and uh, get into biomass as depicted by this picture here. By a good pretreatment, you are disrupting the original structure or orientation between hemicellulose, cellulose, and lignin so that you have access to these polymers. Okay, once you get access to these polymers, you can then send them to next step downstream for conversion. As you see in this structure, you can see the lignin is distorted. Hemicellulose is kind of broken into a smaller hemicellulose, and you can see that, for example, crystallinity of cellulose is damaged. Most of the cellulose has become amorphous. It was I think it was Andres who asked me yesterday about crystallinity of cellulose. Yes, it was he asked me, is is cellulose resistant because of its crystallinity? I said yes, and you can see here that by good pre-treatment, you can change crystallinity of cellulose and make it like an amorph material, and then it's easy for downstream extraction. Again, I want to emphasize that uh, in biomass conversion, one of the one of the main objectives, in fact, of biomass conversion is to really extract cellulose and hemicellulose and separate them from the lignin. Okay, because lignin is a tough material. So you will see later on that once you have this kind of situation, there are several techniques where they use to extract and separate cellulose and hemicellulose from lignin. By the way, this picture, this table here is very interesting. In this table, you have a list of several biomass material, and you can see that cellulose, hemicellulose, and lignin are there with different mass fractions. But beside cellulose, hemicellulose, and lignin, if you remember yesterday, I said we have also ash in biomass. Ash is usually potassium, calcium, sodium, and sometimes silicon and phosphorus. Uh, that could be a problematic, especially in high temperature processings. And also we have some moisture. Moisture is a big issue in biomass, and we are going to discuss it today. Uh, Before I go to the next slide, please pay attention that in slides I have put some references. Please, please go and check out these references because they are extremely important. And some of the discussion that we have are better discussed with more elaboration in these references. Just click on the link and go to that reference. You get more insights into what we have discussed in the class. And maybe I will add some questions from these references. So be careful. Be careful is not like a warning. Don't panic. It's just a precaution that these are part of the course. So just to wrap up, what happens to a biomass after pretreatment? So again, as I said, crystallinity of the cellulose would change. The degree of polymerization of the cellulose, hemicellulose, and lignin will change. The structure of lignin change, as you saw in the picture previously. So the lignin is disrupted, and it gains a new structure, and solubilization of hemicellulose improves usually because this is one of the objectives. Also, you will be able to digest cellulose into uh, uh, next processing step. But I have one question for you. I might ask you in next session. Here we are saying here we are talking about solubility of hemocellulose and digestion of cellulose. I want one of you to answer me next time. What does it mean? What is the difference between solubility and digestion? Okay, because basically both of it looks like both mean the same thing. When we say digestion, it means that you want to transfer something from liquid state into solid state. Okay, but what is the difference with solubility? Why we say
Excuse me,
yeah.
Professor. I think one of them is kind of physical changes, physical processes. One of them digestive. When you digest something, the chemical properties of that material may change,
Okay,
and it
but
is kind of
Nazan,
chemical.
let's talk over it next time.
Okay.
Yeah, I okay, that's good answer, but let's talk it next time. I want everybody to think about it because these are some specific terms that we hear in the course. Solubilization or digestion. These are terms that we hear, but and it's important that we get familiarized with the terminologies in biomass conversion. Okay, there is one important step before pre-treatment. So let's flash back to biomass itself. Before you do any pre-treatment to biomass, to any type of biomass, let's think about something very important. It is the fact that usually biorefineries are designed to operate continuously during the year. On the other hand, the harvesting of the crops is a seasonal fashion. So, uh, for example, as you know, in winter there is no harvesting, right? But biorefinery has to operate even in winter. So we have to do another steps before pre-treatment, and we call them entreposage et conditionnement or storage and conditioning of biomass. So, in other words, we have to store biomass somewhere safely, but we have to consider that usually biomass has humidity, it has moisture, okay? And uh, if you want to do any kind of conditioning, or if you have to do drawing in order to reduce the water content, uh, you have to pay. The process becomes a bit expensive. Some people they forget about this step in biomass conversion. Okay, when they do their process design, for example, process design economic calculations, you have to consider storage, and also you have to know that during the storage, maybe you lose some material after you have dried them, so you lose some material. So there is no choice. Uh, you have to store your biomass nicely, but you have to pay attention to one thing important. The quality of the biomass has to be preserved. You cannot do any type of storage that can damage the quality of the biomass for the uh, process conversion plant. Anyway, there are typically some there are some storage and conditioning uh, practices. The most common ones are listed in this table. One of them is enlisage. It is a kind of anaerobic fermentation process. So they they apply kind of fermentation process to biomass in order to protect the biomass for some time. This is the practice that usually traditionally is done for domestic animals to provide their food. But by doing so, your biomass will be in the humid environment, will become humid. So this could be a challenge. Just pay attention because next time we are going to talk about this, the moisture of biomass. Another technique of conditioning biomass is to add specific chemicals. For example, they add some phosphate chemicals in order to neutralize the conditioning of biomass, but that process is kind of expensive. Another way is to, uh, again, by the way, even by chemical treatment, the biomass will end up with a uh, humid situation. Another technique for conditioning is séchage or drying. So they apply drying in order to reduce the humidity of biomass to 8 to 20%. But again, drying, you have to consume energy, so it is energetic. It is, I mean, it is energy, um, uh, uh, energy demanding process and expensive. Couture. Okay, so we flash back to uh, storage and condition biomass. Now let's continue about pre-treatment. So there are usually three main uh, pre-treatments on biomass: physical treatment, chemical treatment, and thermochemical treatment. Physical treatment is, for example, for to reduce the size of biomass, like by grinding. But of course, there are other methods that we will discuss later, like densification and drying. Chemical methods are to modify the structure of biomass in order to extract certain components of biomass by in presence of acids, base, and solvents. Okay, and by in thermochemical processing, usually they want to modify the structure of biomass with the combination of heat and pressure. Okay, but of course there is a I can say there is a fourth method of pre-treatment, which is the biological treatment. Pre-treatment. In other words, they add bacteria, for example, to biomass for to preserve the biomass for specific applications downstream. Now let's talk about what time is it? Okay, I think part of the second part of the course I have to teach it next time. But anyway, at least I'm happy now that I explained. I emphasize enough on importance of biomass and its pre-treatment because once you know at the beginning what it is, the rest of the story is easy to follow. Okay, now let's talk about physical pre-treatment and conversion of biomass. The very first parameter of biomass, I mean physical property of biomass that we are going to discuss is heating value of biomass. In French, we say pouvoir calorifique, heating value of biomass. Why it is important? Because as we said many times from the beginning of the class, then one of the main reasons to use biomass is to produce energy products. Okay, energy. Okay, so it is important to consider biomass and its heating values. So this table has listed some heating value, high heating values of biomass in terms of kilojoule per kilogram. So heating value, as we said yesterday, is energy content of the biomass per unit of mass, so that if you burn the biomass, that energy will be released. As you know, combustion is the exothermic process, and you release energy by combustion. So that's why heating value is important. So there are different ways for measuring heating value of biomass. One way is by doing some um, formula that exists in literature, like the one that is listed here, based on elemental composition of biomass, carbon, hydrogen, oxygen, even sulfur. I want you to really uh, take this formula in your equation because you might use in your exam and in your homeworks. There is another method also by this simple equation. You can follow notes here to understand how they work, and you can also use these websites to better understand how we can calculate heating value of biomass and any other sort of fuel. But experimentally, usually we use a bone colorimeter in the lab, at the lab to measure uh, high heating value of uh, biomass. But there is something important I want to focus here. Usually, when we talk about heating value of any fuel, we have high heating value and low heating value of any fuel. So, in terms of biomass, we have pouvoir calorifique élevé or pouvoir calorifique inférieur, heating, high heating value and low heating value. So, what is the definition of low heating value and high heating value? Imagine that your biomass is completely dry. There is no moisture inside the biomass. So, um, uh, heating value is the value that you calculate by Bohm colorimeter, for example. But as you know, during the combustion of any fuel, you produce some water, and that water takes some energy. I mean, takes latent heat energy uh, in order to evaporate. So by taking into account the heat of evaporation of water produced during combustion, okay, in this equation you deduce it from HHV, high heating value, and you calculate low heating value. So in other words, low heating value is the energy value by disregarding the evaporation energy of water that produced during combustion of the fuel. Okay, so there is the equation is written here. It's very simple equation. But what you have to notice is that usually in any fuel, let's say even biomass, you have usually halogens like chlorine and fluorine. By having these kind of halogens during the combustion, they can consume some part of the hydrogen of the fuel. For example, Cl reacts with hydrogen and produces HCl. So, if you want to have an idea of how to calculate the partial pressure of hydrogen of water in this equation, you need to use this equation by taking into account the elemental composition of the halogens. Okay, so anyway, this formula is about a relation between low heating value and high heating value in dry mode. But as I said before, in biomass, you have some moisture itself, some moisture. So if you want to have a real and low heating value of biomass, okay, you have to consider mass fraction of moisture in the biomass as well. So this formula at the bottom uh, shows you how to calculate low heating value by knowing the high heating value and uh, moisture content of the biomass. But if you remember, we said that in we said here that in the conditioning you are applying some conditioning methods in order to store your biomass for some time. So you are adding water anyway to the biomass. So as you will see later, having moisture content, having any water with biomass decreases the low heat value of biomass. In other words, you have to do drying to get rid of the water content. But before we reach that point about drawing, let's have a look at this very interesting diagram. This diagram is comparing different fuels from biomass, peat, brown coal, coal, and anthracite, okay, with respect to elemental composition. So when I say elemental composition, I mean elemental oxygen most of the time, elemental carbon, elemental hydrogen, and again elemental carbon. In this diagram, on in x-axis, we have a mass ratio of elemental oxygen on elemental carbon, and in y-axis, you have mass ratio of elemental hydrogen over elemental carbon. Okay, and it's very interesting. As you know, in for example, in coal, oxygen content of coal is very low. That's why you see that coal is in this region. But most of the biomass is in this region because it has more oxygen content in it. We have more like 40 to 50% elemental oxygen in biomass. Okay, so this the graph shows you uh, uh, a kind of a spatial location of biomass. I mean, different fuels, fossil or renewable fuels, with respect to elemental composition. But most importantly, it shows you how they are the low heating value is associated with these kind of fuels. You can see that, for example, uh, in coal that you have less oxygen, your low heating value is much higher than a biomass that has higher oxygen content with the low LHV, low heating value of 16. Okay, because you know that the less oxygen you have, it means you have more carbon, so you burn more carbon because combustion is a reaction between oxygen and carbon. Okay, that's the concept behind why biomass has less LHV compared to coal, because in coal you have more carbon compared to oxygen. But maybe you have maybe it is your question that why you are showing a region for each fuel. It's like an area, not just a single point. It's because, as I have said several times so far, uh, fuels, they don't have fixed chemical composition. The chemical composition of fuels varies from location to location, even from type to type. So that's why we identify the kind of area for each fuel. Okay. By the way, you have an idea of LHP of biomass compared to LHP, for example, of anthracite, which is a very high quality coal. Okay, now let's talk more specifically about now humidity in low heating value of biomass. As you see in this picture, in this diagram, I mean, if you apply drying to a biomass and reduce the moisture content of biomass from 50% to 35%, the energy value, the low heating value of biomass increases uh, from 20 to 30%. So it is therefore important to reduce water content of biomass in order to gain a more energetic uh, biomass. By the way, there is a very interesting document. I want you to please click on this link later on and study different aspects of biomass drawing. It's a very interesting document. So I want to talk about biomass drawing, but let's have a 10 minutes break. We can come back. Okay, it's 1:44 almost. Let's be back around yeah 1:55, almost 10 minutes. Let's come back and we continue the rest of the course. If anybody has a question, please let me know.
Yes, sir. I have a small question.
As
Um,
usual.
yes,
But
I'm sorry.
I really like Amrez your attitude that always you ask question. I really like it. I wish everybody
Yeah,
could
guys,
have it.
I'm trying to remember a
That's
lot of
good, very
things.
good. I really like it.
Uh, okay, my question is about the high heat value. So I have in mind that sometimes not in biomass products. I mean, in, for example, with methane or any organic compound, the heat, the high heat value, I can assume that is the same combustion enthalpy, and sometimes to calculate the high heat value.
Uh, Heating value?
Yes, I
Yes
mean,
and no. Yes and no. Why? Because when you consider a fuel, it's not just, for example, methane. It has
okay,
other. It can have other chemicals. Okay.
okay,
Of course, heating value is obtained by combustion. It's combustion, right?
okay, okay.
But your fuel is not necessarily methane. It has methane, ethane, other
Yeah.
gases.
So
So
assuming that it's,
that's
for
why.
example, you give me a problem with, I don't know, propane, for example,
Yeah,
or
it's energy.
butane,
It's,
I don't
it's
know.
combustion. Yes, energy
Okay,
of combustion.
okay, 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 okay.
And
Oh,
if you look at the formula that I
yeah, yeah, I'm
presented,
looking at it.
you can see the body. I mean, you can see that it. For example, the ash content, sulfur content, they have impacts. So these are the things that impact the calculation of heating value, because uh, because uh, for example, if you have sulfur, oxygen reacts with sulfur, you produce SOx, SO2, SO3. Okay,
Yeah,
so I mean there could be a difference between combustion. I mean the energy of combustion, for example, of methane, and the heating value of the natural gas that you
yeah.
calculate by Bohm parameter, whatever. But they should be almost similar.
Okay, okay, okay. So in that case, I can not use this formula for uh, organic compounds. I mean, for methane, for example.
Yes, you
I
can.
can, I, okay. Oh, okay, having all the mixture, not just
Yeah,
CH4.
yeah, yeah.
That's the condition.
If
Ah, okay.
if you have a if you have a mixture and you want to measure its energy, uh, okay, I mean heating. As I said, heating value is a kind of integrated amount of enthalpy of combustion. Integrated,
Yeah,
okay. But
yeah,
for
I
each
get it. Yeah.
specific reaction, you need to consider its own delta H.
Okay, okay. That gives me a lot of
But it was a good question.
clarifications.
Yeah.
Thank you so much, sir.
Okay.
Okay.
Okay, I stopped my microphone just for a moment. I'll be back at 1:54. Okay, uh, let's start. So, Sarah, did you get why we need to do, for example, drawing on biomass?
Yes, because the water will decrease the heating value if you have.
Yeah.
Uh,
Okay, that's good. That's good. So, again, we are not talking about thermal, physical treatments or pre-treatments of biomass. There are two sources here. I really again want you to go through and get familiarized with different drawing methods, because now we are talking about drawing of biomass. There is, just to give you an impression of biomass of I mean drawing plants. I want to click on this uh, file here. Uh, Actually, I had opened it already here. Just look at this video just a moment. You can see that a drawing plant can be a really large unit. You can see that before I go to slides. Yeah, here this is the dryer. This is the rotating drum dryer. You can see how large it is. You can see from the video when they are turning. You can see the movement of biomass. This is a kind of bundle tube for indirect heating of biomass. So in these bundles, air or steam goes through inside the tubes. So you have indirect contact between biomass and source of energy. And you can see anyway that in a drawing in drawing uh, we have you can have complex units of operation. It's more complex that that you can imagine. It's not just simple oven you put there and you get your sample dried. Because drying is very important and very energy uh, consuming operation in any plant, in mineral processing, biomass conversion, in pharmaceutical, in petrochemical, everywhere. Drying is important, and you can see um, how big the dryers are. This is the dryer. You can imagine how big it is. It's a rotating drum. These are, yeah. I want to show you Yeah, these are the biomass, for example. You can see that they are dumping biomass into the wire. Yeah, I wanted to stop here. So you see inside the dryer, you see these tubes. This is interesting because this is a special dryer for indirect the drying of biomass. So these are the tubes inside which air or steam can flow, but biomass is in between in the shell of the dryer. So there is a kind of indirect exchange of heat in these kind of rotary drums. But you can imagine, just imagine size of the tires of this conveyor compared to size, the diameter of this dryer. You can see how large a dryer can be. So they are interesting unit of operations that I wanted to share with you. So you can get an idea of importance of drawing. So uh, the link is here. You can go to website of this company. It's a German company. They make various sorts of dryers. And again, this document is interesting for some more insights into the concepts of drawing. So I'm going to go a bit quick on drawing because we don't really have time. Drawing itself can be a course. It's a very important process operation. So as you saw you watched on the video, one sort of dryer is rotating dryer. It's a rotating drum, as also you can see in this picture. And heating can be direct or indirect. I show you that picture how indirect looks like by those two bundles. So the intense temperature of the heat source, which is air, hot air or steam, is usually 300 to 600 Celsius. And so usually the energy demand for is like a 1000 kilowatt hour per ton of evaporated water. Usually there is a very good heat transfer inside these rotary drums, but one challenge is the emission of organic materials and dust that can be produced in these rotary drums. Yeah, this picture is a bit more clear. So imagine that, for example, this is a rotary drum, so rotates. The drum rotates radially, and wet biomass is added to the entrance of rotary, and also you have the hot flue gas, for example. Due to the fact that in biomass we have always some volatile composition, so under drying those volatiles evaporate, and so they make smells, and sometimes they are toxic. Plus, the biomass itself after drying can be broken into a smaller parts, so you have dust production. Therefore, in the exit of the dryer, usually we need to have a air and solid cyclone. And also at the end, here is the stack, but it's better to before the stack there should be a special, for example, absorption column, something in order to absorb or condense those evaporated volatiles from biomass. Another sort of biomass dryers are tubular dryers, which are mostly fluidized beds, leaf fluidized. Fluidized beds are important gas solid operations for in chemical industry, in mineral processing, pharmaceutical. Biomass are extremely important. Hopefully, during the course, I will provide a session so I can teach you a little bit on fundamentals of fluidization. I don't. It's a big topic, But just keep in your mind that in a fluidized bed, for example, so you have a bed of small particles of biomass. They cannot be large parts. They have to be small parts of biomass, small particles. Then the hot air goes through. Particles are getting mixed, so they are mixed together. So you have a good contact between hot air and biomass particles in order to be dried out. Another type of biomass dryer, in general, any type of dryer is called superheat drying with superheat steam or superheat dryers. So in superheat steam, which could be batch mode or continuous mode, usually the superheat steam gets in contact with the biomass. Sometimes especially when the operation is a batch mode, you have high pressure, so you end up with a pressure of 2 to 5 bars, but within 5 to 60 seconds, quite short. And with that contact between the superheated steam and biomass at temperatures from 115 to 140 Celsius, you dry uh, biomass. Another sort of biomass dryer is flash dryer, séchoir à flash. Uh, so in flash dryer there is a very uh, fast, I can say, fast contact between the steam and biomass. That's when we say flash, it means something is fast. So for example, in this case you can see that this is the structure of flash dryer. You can see that here feed is added to this horizontal column. In the horizontal column, so the feed is gets kicked out by a very high velocity of hot flue gas, okay, and then they go into this vertical column. In here there is a, it's a kind of transportation regime in fluidization. There is a very good contact between the solid biomass and hot gas, and at the end the dry biomass is recovered by one or several uh, types of air and gas cyclone. So the solid biomass after drying is deposited or recovered at the exit of the deep leg of cyclone, and in the outlet of the cyclone the steam is out. So this is so when we say flash, it's about the fast contact between biomass and hot air. Usually it is air, the flue gas. And when we say uh, flash, it means that the flow rate here is really really high. So in a matter of seconds, the drawing happens. Another type of biomass drawing is séchoir à bande, or drawing on a carrier, for example. As you see, this is I mean, on a conveyor. This is a conveyor that is carrying the biomass horizontally. Usually, under these conditions, I mean, on these unit of operations, temperature is around 90 to 100 degrees C. So, one advantage of having this kind of low temperature is that you don't produce those smelly materials, and you don't produce that much dust. So it is uh, in terms of dust and making a smell, it is more promising, but it takes a longer time, of course, in terms of uh, operation time. So uh, after drying, or maybe I can say before drying, uh, we had to ask ourselves something. What is the size of the biomass that we are going to dry? Or, for example, if you have a piece of a long piece of tree that you have cut in the forest, how do you dry it? So that's the question. Usually, it's better to first reduce the size of the uh, biomass and then do drying, because then it will be efficient. So in general, uh, uh, grinding is very important. Is a very important physical operation on any solid material. Either it is or minerai en français, or uh, catalyst, or it is a biomass. Always you have to cut. So there are many reasons actually. Not many. There are some important reasons, 4 or 5 reasons to reduce the size of the solids. One is to make transportation easy. Okay, so if you cut your biomass into smaller pieces, transportation handling is very easy. Second reason is that by cutting, you are uh, maybe you are increasing the surface area in the downstream conversion reactors. And another reason is, for example, in terms of biomass, by special grinding, you are changing crystal structure of cellulose, uh, and there are some other reasons. But the main reason for grinding is to make the handling and transportation easy, and to increase contact with to improve the contact between biomass and chemical reactants in conversion unit operations. Okay, so uh, anyway, for those who don't understand French, broyage means grinding in French. But in grinding, even though it is important, it takes a lot of energy. It's a very energy demanding unit of operation. And people who design grinders, they have to really be careful to have a very good estimation of energy requirement in their grindings. And there are many designs of grinders. Last semester, some students had the course of mineral processing with me. In more detail, we discussed about different sorts of crushers, grinders. Unfortunately, most of you didn't attend my class. We don't have enough time, but if later, if you wanted to have more information, let me know. I will share my course notes on mineral processing so you can have a good idea of uh, grinding. But specifically about biomass grinding, the efficiency of biomass grinding, or or in particular, the energy consumption in grinding of biomass depends on some factors such as type of the biomass, humidity of the biomass, granulometry of biomass, I mean, in other words, shape of the biomass, density of the biomass, and the type of the grinding equipment that you use, also the flow rate of feeding. These are all important parameters for biomass conversion. So, as I said, there are some descriptions here of some different sorts of biomass grinders, like disc, drum, and screw grinders, or shear grinders, hammer grinders. I really want you to click on the link here to go and get some ideas of different sorts of biomass grinders. But uh, I just want to show this video to get an idea of how a grinder can really help. Just watch this video for a moment. This is the grinder mounted on this truck. You can see wood logs are uh, uh, imported to grinder. They are large logs, but at the exit, you see, you have very small particles of biomass. So you can imagine how grinding is important. It's not really a big equipment. It's quite small, but the efficiency of grinding, I mean the impact of grinding in the overall biomass conversion is very high. You are converting such a large biomass, woody biomass, into really small particles. So transportation is very easier because they become very flowable, and a lot of transportation handling issues are solved. Plus many other advantages in terms of reactivity with the reagents in downstream reactors. Okay, let me go back to the course. Uh, Here I just want to talk about one specific case that is reported in the article here. Please click on the link to get through to understand how the experimental setup was used to investigate different parameters in biomass grinding. So this is a very small lab scale experimental setup. There is a hammer grinder here, and there is my screen. The screen has some holes. Some of you already know what are the screens or sieves. So biomass used to be feeding from the top, and the hammers of this hammer grinder is applying force to biomass, so they become smaller particles, and then they get discharged from the holes of this screen, and then back to a cyclone in order to separate solids from gas. By the way, I have to tell you, once I teach the course on fluidization, I'll talk also about cyclone. Cyclones are very, very important unit operations in biomass conversion in any solid handling operation, because cyclones are to recover solids from gas, and in case of the liquid, we have hydrocyclones we use to separate solids from the liquids. They are very important. Uh, so anyway, back to the course. In this table, the researchers reported impact of grinding on different source of biomass like wheat straw, barley, corn, stover, and switchgrass with different moisture content and with different uh, sizes. So I don't want to go all to details. You can yourself look at it. But what I want to emphasize is that you can see that uh, the average specific energy consumption uh, is different for each sort of biomass. You can see, for example, corn stover, less energy requires compared to wheat straw, for example. Okay, and also we can see that in terms of moisture content, in terms of moisture content, you can see that if you compare, for example, this value to this value, the moisture depending on the moisture content, the energy requirement is also different. I expected myself that with higher moisture, you need to have uh, higher energy consumed, but the data of this table on average shows that less energy was required when you have higher moisture. I don't really. I'm researcher. I prefer to do my own research, but this is what is reported in this report. So anyway, what the message of this table is that uh, grinding, the energy consumption in grinding really depends on type of biomass, moisture content, uh, and of course, in this specific publication, they use only a hammer mill, a hammer grinder. If they change the type of the hammer, or even they change the type of the mill itself, the results will be different. For example, if they in their own example here, they just changed the opening of the screens below the hammer. and by changing the openings, the values of energy consumption differ. So I want you to go to to read the article and get familiar yourself with more insights into grinding and affect and associated parameters. So here is the list of some suppliers of grinding in Quebec if you are interested. It's not important for the course. Okay, now we want to talk about something really important in terms of density of biomass. Before we talk about the density of biomass more specifically, let's talk about definition of density. Okay, because some people really don't know the difference between the densities. Usually, we know that density is the volumetric mass of any material, amount of mass per unit of volume. We know that. Then is always, for example, the unit is kilogram per cubic meter. We all know, but the thing is, we have three different types of density. We have bulk density, okay? Okay, the bulk density itself has two types. We have two types of density, which we call it density at minimum fluidization or aerated density, aerated bulk density, and a tap density, which means that if you have a group of particle, you just tap the vessel so all the air molecules are out as much as possible, so particles they get as close as possible. That's okay. So when we say bulk density, anyway, it means when you have a group of particles together and you want to know and so they form a volume and you want to know what is the mass of the particles in that volume of the group of particles. So definitely particles, I mean there is voidage, there is empty space between particles due to the gas or liquid, whatever. This is the bulk. So when we say bulk density, it means uh, mass of a group of particles in a specific volume. But what about a single particle itself? When we talk about a single particle, not a group of particles, you have two definitions: grain or particle density and skeletal density. So if your particle is not a porous particle, these two are similar. But if your particle is porous, it has porosity, like the shape here. So you have empty voids inside the particle itself. Here uh, the definition of density is, uh, I mean, the definition of particle density is the total volume of the particle, regardless of the empty spaces. We ignore them. So the total volume. So the mass per this total volume is called the grain or particle density. But if you want to be very specific and you want to really take into consideration the empty space or the voids inside the particles and decrease that volume from the total volume of particle, then you are in fact calculating the skeletal density. So a skeletal density is mass of the particle per real volume of the particle occupied by the solid, not by gas. So if you want to compare the value of the densities, usually a skeletal density is more than particle density and more than bulk density. Okay. So talking about bulk density, uh, we are talking about biomass. Okay. Biomass usually has very low density, and um, when you are dealing with I mean a skeletal density or even particle density of biomass already is quite low. Okay, and if you have a bulk of biomass particles together, usually you end up with a large volume. I remember when I was a kid, They used to my family used to ask me, do you think 1 kilogram of iron is heavier or 1 kilogram of cotton? And this was a very smart question, and most of the kids they answer by mistake. They say iron 1 kilogram of iron is heavier. Okay, but it's very interesting question. Of course, in terms of kilogram, 1 kilogram of cotton is equal to 1 kilogram of iron, but the volume of 1 kilogram of cotton is much more than 1 kilogram volume, the volume of 1 kilogram of iron, because cotton, which is a biomass, has much less density than iron. Okay, so I really want to emphasize on that. In biomass, we have the issue of low density of the single particles, and specifically when they are the bulk, when they have a bulk of the biomass, even worse. So if you are dealing with this kind of situation, again, in terms of process, your process can be expensive because, for example, if you want to transport biomass from agricultural field to a central biorefinery, you have to use a lot of trucks, for example. So transportation is going to be expensive because uh, you load your trucks very quickly just adding a little bit of mass. So this is why one of the pre-treatments that we have to do on biomass is called densification of biomass. So in other words, densification of biomass means to make the biomass dense and dense and dense as much as possible, so the volumetric mass of the biomass could be much smaller. Okay, that's the main reason for uh, densification, as listed in this slide here. But by the way, another important uh, aspects of biomass densification is to increase the quantity of the energy per unit volume. If you look at these three cubes, it's very interesting. Uh, for similar energy per volume, uh, okay, and if you, I mean, for a specific energy, in other words, you need to have larger volume of, for example, pie or straw compared to wood and compared to coal. Okay, this schematic is very interesting. Gives you an idea. If you want to have a fuel similar to fossil fuel and get benefits of that biomass, you need to densify it. You need to make sure that the amount of energy per unit volume is similar to the one of fossil fuels. So you have to do a densification. So there are different techniques for biomass densification. Uh, I don't want to go to details of these techniques. Just I want to briefly tell you what they are. So in terms of there are mechanical and chemical densifications. In terms of mechanical densification, one of them is to make bales. I'm sure you have seen these bales in farmlands. So they are the very traditional ways of making these kind of groups of biomass, large groups together. Usually they are large, 1.2 meter, for example, to 1.5 meter, and they could be cubical or spherical. But mostly in terms of biomass conversion, uh, they tend to make pellets of biomass. So what it is done is that we use specific binders, and we make pelletization. We make pellets of biomass. So each single pellet that you see here, for example, is a group of many biomass particles. But pelletization can be in different forms. It can be cubical, it can be in the form of briquettes, or even in the form of pucks. Pucks are like a hockey pucks. They have like almost 7.5 centimeter, but narrow thickness. Or sometimes you just make wood chips to make densified. So there are several techniques, unit operations to make these equipment. I really suggest that you go and study on your own to make yourself familiar with the different techniques, different, equipment that people use in industry to make pellets or cubes of biomass. But beside the mechanical densification techniques, there are uh, chemical, I can say thermochemical techniques. That in general they are pyrolysis. Next week, Professor Shauki will explain more things about pyrolysis. Myself also later I will discuss. We will discuss anyway more about the pyrolysis. But in terms of pre-treatment, there are three types of pre-treatment in general that is applied to biomass. One of them is torrefaction. So what is a torrefaction? I'm sorry. So first I have to say what is pyrolysis. So pyrolysis in general means a thermal treatment of a fuel in the absence of oxygen. So there is no oxygen. Usually it's under inert condition like nitrogen. You have a flow of nitrogen, so you have no oxygen, because if you have oxygen, you will combust your fuels. You don't want to burn them. So pyrolysis, depending on the level of temperature, could be depending on level of temperature and also the operation time, is could be torrefaction, slow pyrolysis, and fast pyrolysis. So in torrefaction, usually temperature is about 280 to 320 Celsius, and usually reaction time is a matter of few minutes. What happens to torrefaction is that in torrefaction, some of the volatiles of the biomass is evaporated, and the remaining biomass becomes very resistant to biological attacks and moisture. Okay, so for example, for storage is good, and um, it is it is very important that they become also very hydrophobe. So again, for example, if you are in Canada or in a country where, yeah, you receive a lot of rain, you have a lot of snow, your moisture, or you have a humid weather in summer, torrefaction is a very important technique, because by torrefaction, your biomass becomes hydrophobe, so it doesn't absorb water. So for storage is interesting. Slow pyrolysis is similar to torrefaction, but a little bit temperature is higher, 350 Celsius to 500 Celsius, and longer reaction times from 30 minutes to 2 hours. But the one difference between torrefaction and pyrolysis is that in pyrolysis, almost everything is converted to a charcoal. In other words, the main product of slow pyrolysis is the charcoal. The charcoal that you use, for example, to make barbecue comes from here, slow pyrolysis. Okay, so the main product of a slow pyrolysis is the charcoal that you have it here in the picture. Another technique for densification of biomass is fast pyrolysis. In fast pyrolysis, usually temperature is higher than slow pyrolysis, 450 to 500 Celsius, and it's very important here. Reaction time is very fast, 1 to 2 seconds, very fast. Okay, so reaction time is very low, and the main product in fast pyrolysis is bio oil. In other words, when you do fast pyrolysis, most of the biomass is evaporated. So the evaporated gases will be condensed after the pyrolysis reactor, and that condensed product, we call it bio oil. and it is usually 75%. And the bio oil usually uh, has much more energy and density than biomass itself. Of course, you have also some charcoal that remains inside the reactor, but just 10 to 15%, depends on the biomass. So I hope you understood what is torrefaction, what is a slow pyrolysis, and what is fast pyrolysis. They are very important unit operations. Tens of articles and research have been done on these techniques. Just to give you an idea about the energy, so imagine that you have one biomass with mass volume, with density or mass volumic of 60 to 80 kilogram per cubic meter. Just look at the data here, depending on the mechanical or thermochemical densification that you apply, the volumetric mass or density is drastically increased. And interestingly, for example, in terms of bio oil, so if you do fast pyrolysis, you get a material that is energy, that is the density is much higher than the original biomass. This data is very, very interesting, and I want you to really pay attention. So this graph shows the trend from another perspective. So you see that it just compares the energy, again, the density of the material. It just shows that what is the impact. So if you produce bio oil, you obtain larger density. But if you just apply just grinding, like making wood chips, the mass density uh, is not that much improved. So it just tells you the impact of densification. When you do briquettes, pelletization, cubes, whatever, you can see again increase of the density starts. In Canada itself is the large producer of uh, pellets of wood with the production capacity of 3 to 4 million ton per year. 84% of the wood pellets that Canada produces is exported to Europe, and in that the economy of the this kind of market in 2012 was $208 million. Just imagine, just by pelletization of the wood, how much money you can make. So we don't have enough time now. We can talk about hydrolysis as a chemical pretreatment next time. Uh, I hope you understood at least the physical pretreatment techniques. If any question, I'm here to answer your questions. Let me stop.